Hey, hello everyone. Sorry I'm not there today, but we can still move on with our actual content for the class. So the first thing going to talk about are early atomic theories and kind of how we came to the quantum theory of how electrons behave. So you've heard a lot of this before in your science classes. So I'm going to kind of breeze through the first bit here before we start to get to like wave particle duality. Okay. So the first person to actually kind of come up with the idea of an atom being the building block of everything was Demetrius. He was an ancient Greek back in about 460 years BC. So he's a Greek philosopher, and he hypothesized that matter was could be cut into smaller and smaller pieces, and eventually we would get to a point where you can't cut it any smaller. Okay, it can no longer be divided in half. So you go half, 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 half. Eventually, you can't cut it in half anymore. Okay, and then he called these particles like atomos in Greek, but they're atoms, which just meant that they're indivisible. Okay, so you couldn't cut them any smaller. But he was kind of like turned aside this theory because the prominent people at the time, like Aristotle, believed in like the four element theory, which was like everything's made up of like earth, air, wind, and earth, air, water, and fire. So no one really believed them, and it was like not even considered for almost 2,000 years until we get to John Dalton. Okay, and he proposed the first modern atomic theory based on results from his experiments. Okay, so he conceptualized it was called like the billiard ball theory, but that everything is made up of these small spheres called atoms. Okay, so it took almost 2,000 years for us to kind of realize, okay, everything's not made up of earth, air, fire, and water. Okay, so the main points of this theory was that matter consists of definite particles called atoms that cannot be divided. Each element is made up of its own kind of atom. Atoms cannot be created or destroyed, so that was a pretty unique thing for the time. And atoms join together in small whole number combinations to form compounds. Okay, so a lot of the stuff that he kind of thought of uh, is still accurate, and we've only built upon Dalton's theory as we've gone on in the past 200-ish years. Okay, so the next person to develop on or kind of build upon Dalton's theory was J.J. Thomson. So he did these experiments using cathode ray tubes, and what these were is that you had a glass cylinder here where almost all the gas was removed out of there, and you had these charged plates. Okay, and then what you would do is when you turn on an electrical source, it would run a little current through here, and you would shoot a beam of they weren't sure what it was. Okay, they shot a beam of particles. Okay, not sure, not fully understanding what they were doing. Uh, when you run electrical charge through here, if the plates weren't charged at all, the beam would go straight and it would hit the back of the tube. But when the plates were charged, the beam would go through and then it would actually bend and hit somewhere else in the cathode ray tube. Okay, so they would bend towards the positive terminal. Okay, towards the cathode part, not the anode. Okay, the positive portion of it. So he knows the bending and he saw where it went. So this kind of helps him to conclude that the particles found producing the ray were negatively charged, okay, and were a lot smaller and lighter than the atoms because A, they bent towards the positive end, and B, they're able to actually move, okay, they weren't still going directly straight, okay. So the particles were later named electrons, and you may remember from like grade 9 science, Thomson proposed the race and button model of the atom, okay. So you have this big positive sphere with little tiny negative bits of energy called electrons. Okay. Next, we're going to get into radioactivity. Discovered in the 19th century, scientists discovered certain elements emitted high levels of energy. So scientists like Madame Curie, Mary Curie, She did a lot of work with radioactivity. Okay, and then also Henry Becquerel, and Becquerel is actually the units for radioactivities. Becquerel BQs. Uh, that's actually a unit of radiation. Okay, so he found that minerals containing uranium produce an image on a photographic plate. Okay, elements that emit radiation said to be radioactive, and radioactivity is the spontaneous decay of the nucleus of an atom. Okay, so we still don't quite have the nucleus yet in our atomic theory, but they discovered radioactivity. Okay, Rutherford comes along, sorry, and he discovers the nucleus with his famous gold foil experiment, which you probably heard about in grade 9. Okay, so he's polonium as a radioactive source. Okay, so that's why we discovered radioactivity, and that led to these new experiments. Okay, like this one. Uh, so polonium would emit high-speed, positively charged alpha particles towards a sheet of gold. Okay, so we have a stream of alpha particles, and most would go through the foil no problem, but then a few of the particles bounce back. Okay, they got ricocheted either back or they got kind of deflected, like they pinged off of something. Okay, so he compared, like, this was very unusual. It was not at all what he was expecting. He compared it to having a shotgun and or like firing a gun at a sheet of paper, and it bounces back at you. Okay, so he expected everything to go through, like the plum pudding model was say. Everything was passes right through, but a small portion of the particles were deflected, indicating that there is a small concentrated positive charge. Okay, so remember, this was a positively charged ray. So if the majority of this is positively charged, it just pass right through. Okay, because there's negative energy in positive space, but there's a small concentration of positive charge, so most of the rays go through no problem. But then some either are bounced back or they get ricocheted off to the side. Okay. So what Rutherford concluded was that an atom's positive charges are concentrated at a small central core called the nucleus. Okay, and then our nucleus is centralized and is surrounded by the electrons in orbit. Okay, it was later suggested by another scientist called James Chadwick that the nucleus also contains neutrons, which are similar in mass to protons, but they don't carry any charge because they recognize that however many like protons being a particle, it didn't kind of equate to the mass of it. Okay, so Chadwick kind of discovered that missing mass would be neutral, and we call them neutrons. Okay, so Rutherford's theory was good, but it has some limitations. Okay, because as an electron orbits the nucleus, it should emit energy in the form of electromagnetic radiation. Okay, just as it orbits, it should be releasing radiation. Okay, and then when an electron runs out of energy, it should collapse back into the nucleus, but atoms are very stable. Okay, so according to his theory, they should be releasing all this energy and then collapse upon itself. But atoms don't. Okay, and they knew that they don't. So they knew that there's something else that they're missing. Okay, so now we're going to take kind of a brief aside and talk about light. Okay, so this part will go a little bit slower just in case you haven't taken a student. Okay, so light energy is electromagnetic radiation. Okay, so we have the whole electromagnetic radiation scale. Okay, and visible light is actually just a small portion of that, but it's all electromagnetic radiation. Okay, because it is a way kind of interweaving waves of electrical and magnetic waves. Okay. So there's been much debate over the nature and properties of light for centuries, including back then. In the mid 19th century, James Maxwell actually proposed the idea of the electromagnetic wave theory and combining the two. And according to this theory, light is an electromagnetic wave that's made up of continuous wavelengths that form a spectrum. Okay, so travels in the form of a wave where we have crests and troughs at the bottom, and from one crest to crest or from one trough is our wavelength. Sorry, yes, I'm still in the call. Thank you. Okay. So Electromagnetic radiation comes in a very, very, very wide range of frequencies and wavelengths. And if you don't remember or haven't learned yet, frequency and wavelengths are inversely proportional. Okay, so frequency is usually given by f. A wavelength is given by the Greek letter lambda, but they are, oops, not equals. I want, okay, whatever, so frequencies are, this just means proportional to 1 over lambda. Okay, so they're inversely proportional to one another. Okay, so this range is referred to as the electromagnetic spectrum. Okay, of all these radiations, we can only sense a very narrow band of them, which in our eyes, which is visible light. So we have radio waves all the way out here, which are kilometers to meters in length and wavelength. That's just wavelength here. Okay, so they're very long wavelengths, and meaning that they have very low frequencies because they're inversely proportional. Then we have microwaves here. Sorry, that's supposed to be mute. Microwaves, which are in micrometers or microns. Okay, this is the wavelengths of Wi-Fi as well, and any kind of like cell phone radiation. So microwaves are in this range too, just below radio waves, and it's obviously where microwaves are used at, and they can be centimeters to micrometers in length. Then we have infrared rays, so that's kind of the energy that we emit just from like heat. So all heat, all thermal energy, is infrared radiation. Okay, and everything below visible light here is what we call non-ionizing. Ionizing. Okay, meaning that if it hits an atom, it's not going to excite it at all, which we're going to talk about excitation in just a minute, but it's not going to affect the electrons at anything. Okay, and then we get into visible light. These are all on the order of nanometers. Okay, red light is about 750 to 700-ish nanometers. And then we get down to violet at about 400 to 450 nanometers in length. Okay, so it's a very narrow range that we can see when we have wavelengths that are kilometers long, all the way down to our gamma rays. It might be on the order of femto, but definitely pico down here. Okay, so next we have UV radiation. Okay, so ultraviolet rays are UV light, like the radiation that we get from the sun, in addition to visible light. Then we have X-rays, which are radiation that we can use in medical procedures. And then gamma rays, which are very high frequency and high energy wavelengths that are very damaging. Okay, so everything here below visible light is called ionizing radiation. Okay, meaning that it can excite electrons, and because it can excite electrons, that's why all these forms of radiation are damaging to us. So, like if you have too much exposure to the sun, you get, or like any artificial UV radiation, you can damage your DNA because you're ionizing the electrons within your DNA, which can cause mutations in your DNA and produce skin cancers. And X-rays, that's why you don't want to have too many X-rays in succession, because it can lead to damages in your body because it will ionize the very atoms within yourself. Okay, and gamma radiation, very high power. Okay, so this kind of leads us into the photoelectric effect. So in 1887, Henrik Hertz, which is the guy, and he's the guy that our unit of frequency, the hertz, is named after. He discovered the photoelectric effect. Okay, so this is when we're shining light on metal surfaces, it can cause the emission of electrons from the surface. So if you shine energy at a metal surface, the electrons can jump off of that metal. Okay, so according to the old classical theory of light that's developed by Isaac Newton, um, the intensity of the light, so like how bright it is, should determine how much energy is released, uh, or how much energy the electrons have once they're emitted. So we have some light shining on the metal surface, and then the electrons jump off. If we make the light brighter, it's going to hit and then jump off faster. That was the old theory of light. However, what Hertz discovered was that it was the intensity of light did nothing. They would always, so if I shine light on this, it would jump off at the same, like if I made it brighter, it would just still jump off. Okay. What actually was is it was the frequency. So he shone different colors at the metal surface, and that would change the amount of energy, the emitted electrons. Okay, so if he would shine red light on the metal surface, they actually the only thing they jumped off. But if he shone green light on them, they would jump off with lower energy, and then if he shone violet light on them, they would jump off with a higher energy. Okay, so this can really confuse scientists at the time because they're like, why is it not the brightness that's doing this? Why is it the color? Okay, so the photoelectric effect was a big problem in science that people were trying to solve. So in 1900, at the turn of the century, Max Planck studied the light that was emitted by odd objects. Okay, so he'd heat up these objects, and it kind of goes into black body radiation a little bit, but he would study heat these objects and then study the effects. Okay, so his experiments led him to hypothesize that electromagnetic radiation is emitted in tiny packets of energy, not a continuous stream. Okay, so instead of just like a continuous stream, or sorry, oops, that. Instead of just like a beam like that, saying waves. Okay, it's in these little bundles of energy. Okay, so here's a little bundle, here's a little bundle, here's a little bundle. Okay, so we have Einstein who comes along and he kind of applies Planck's idea to conclude that the light emitted by a heated solid is called quantized. Okay, so it just means that it's in a bundle. Okay, so it's quantized, it's like kind of localized to one bit. Okay, so one packet or burst of energy is known as a quantum of energy. Okay, so when people start to talk about quantum mechanics, and like you'll see them like in fiction, in movies and TV shows, when transposed sound smart in the movie, they'll say like, yeah, it's a quantum compute. Well, quantum computers are different. Like quantum computers, this whole thing, but it's like it happened a lot on the TV show The Flash. They say like, oh yeah, they're like quantum boots, and like the origin of quantum is just like the burst of energy, and it kind of the duality of the energy. It's not the boots don't, they're not quantum boots. Okay, but that's a different problem entirely. Uh, but then Einstein kind of keeps building upon this, and in 1905, he had the idea of a quantum of energy, and he used this, like he used Planck's idea for the quantum of energy to explain the photoelectric effect. Okay, so we had this problem with photoelectric effects for almost 20 years, and Einstein finally cracks it. Okay, so Einstein proposed that the electromagnetic energy could be viewed as a stream of particles called photons. Okay, so a photon is like a light particle. Okay, so instead of like just being exclusively in a wave, or exclusively as a particle, it's kind of like the wave is a particle. Okay. So he suggested that the electron was emitted from the surface because the metal, or was emitted from the metal because a photon collided with that electron. So you have the electron in orbit, just kind of flying around, and then the photon just happens to go and hit that electron, and that has enough energy within it to knock it out. Okay, so instead of passing right through and missing it, it hits the electron, and the electron jumps off. And just one kind of noteworthy thing is that this is what Einstein won his Nobel Prize for. Einstein won the Nobel Prize for explaining the photoelectric effect. He didn't win his Nobel Prize for his theory of relativity or special relativity. He won it for explaining the photoelectric effect. So that's just a cool trivia note. If you're ever, I don't know, in a trivia contest, if you go on Jeopardy, how about that? If you go on Jeopardy, you should know that. Okay. So if a single electron absorbs a single photon with the right amount of, or with the right quantity of energy, the electron is able to escape. Okay. If the photon doesn't have enough energy, then it won't leave the surface no matter how many photons strike it, because it needs enough energy to get kicked out. Okay. But if you have the same amount of energy hitting it, the electron doesn't care. Okay. It's like a honey badger that way. So photons with high frequencies carry more energies than photons with lower frequencies. So here we have a high wavelength of red light, 700 nanometers, relatively high, but it has a low frequency. Okay, so it hits the metal, but no electrons come out. Okay, then you have kind of median or mid frequency green light. It goes and hits it and ejects the electron with a speed of 2.96 times 10 to the 5 meters per second. Then you have a high frequency wavelength light and violet light, and it ejects the light at 6.22 times 10 to the 5 meters per second. Okay. So why do higher frequencies have more energy than lower frequencies? Because the electron here is just going up and down, up and down, up and down, up and down. Here the electron is going up, down, up, down, up, down, up, down, up, down. Here in violet, the electron is going boom, 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 boom. Because the electron's moving, or kind of, sorry, not the electron, the photon. Because the photon's moving quicker, it's having more energy because it's moving more. So it has a higher kind of, and like, going to say kinetic energy, it's not kinetic energy, but it has a higher energy here moving through, hits the metal, jumps off. Okay, so higher frequency, higher energy. So that kind of brief tangent of light and photons kind of brings us now where we can talk about Bohr's model of the atom. Okay, so Bohr did his work with spectroscopy. Okay, so we've talked about Bohr's model of the atom like throughout high school science, but we haven't really touched on why Bohr found that they're energy shells. Okay, because you don't have the knowledge, the prior knowledge to be able to understand a lot of this stuff. Okay, so spectroscopy is a study of light that's emitted from excited sources. Okay, so light passes through a sample and then it's dispersed through a prism or a diffraction grating to form a spectrum, what we call a spectrum of light. Okay, so when wavelengths of light are represented in an uninterrupted sequence, it's called a continuous spectrum. So that's what the spectrum of white light is. Okay, so if we have a light bulb here, passes through a slit, so we have a single beam, and then passes through a prism. Okay, because all the wavelengths of light have different amounts of energies, different frequencies, they travel at different speeds through the prism. Okay, and should have learned that in grade 10 science, and that's what allows us to get the visible light spectrum. Okay, so this is the spectrum of visible light. Okay, so white light is composed of all the colors of the visible light in equal amounts. But that's not true of everything. Okay, so a line spectrum is what we get when we have something like a pure gas. Okay, like hydrogen or neon. When we look at those, we don't get a continuous spectrum. Okay, so when a pure gas is heated, the atoms of the gas become energized or they become excited. Okay, they just get more energy. Okay, so the gas releases this energy in the form of visible light as the atoms return to a lower energy state. So the atoms will get excited, and then when they come back down to the normal state, they kind of come back to neutral. The energy that they release can actually view as visible light. Okay, so if we have heated hydrogen gas here, and we pass a beam of light through a prism, there's only a few colors that are observed. Okay, and they're just discrete individual lines. Okay, so the series of lines that the element emits is called the atomic line spectrum. Okay, because it's specific to that element. Okay, or specific to that type of atom. Okay, so each element has its own unique spectrum. Okay, it's like a fingerprint for that element. Okay, so the atomic spectrum shows us that an excited atom emits characteristic frequencies of light. Okay, so these are specific to that element. Okay, so therefore there are very specific energy changes that are taking place within the atom. Okay, so this is what Bohr did. Okay, so he heated hydrogen gas and studied that of the spectrum that was emitted by the hydrogen atoms. Okay, and the spectrum indicates that electrons in the hydrogen atom only exist at very specific energy levels. So this is how we get the energy shell levels of the Bohr-Rutherford model of diagrams. Okay, because we see a line here, the violet, another one here, kind of violet, maybe blue. Sorry, I'm not sure how it's coming across on the projector. Hopefully it comes out okay. We got one here, kind of looks green, greeny yellow, and then one here, kind of like the reddy orange section. Okay, so it's not all the colors of the rainbow here. We have very discrete lines. Okay, so then that's how we can see the energy levels that the electrons could be at. Okay, so Bohr studied these banding patterns and came up with this theory that electrons can only have certain amount of energy. Okay, the energy is quantized. It's limited to this specific energy level. Okay, and then each energy level is associated with a definite orbit. Okay, these orbits are called the principal energy levels. Okay, so each one of those lines represents an orbit. Okay, electrons can move in orbits without the loss of energy. Okay, so if I have my first orbit, my second orbit here, the electron can jump up. Okay, so electrons can jump from level to level. They absorb specific quantity of energy when they move outward. Okay, and then release a specific quantity of energy when they move inward. So I have a diagram here on the next slide. So let's say we're talking about the first energy level here, and each energy level increases the amount of energy that there is. So if I have an electron sitting in the first energy shell, and then it gets hit with a photon, it can jump up to the next energy level. Okay, so it's going to be hit with a specific photon of energy, and it can jump up to the next energy level. Okay, then once it's up, this is called the excited state. Okay, so sorry, I should talk about first. When the electron's in its ground state, so that's like its most stable energy level, photon of energy hits it, it jumps up to a higher energy level, and this is when it's in an excited state. Okay, so the electron's so fired up, so pumped to be up here, it's very excited at this energy level. Okay, it's not actually excited, but it's just that's what we call it. That's the excitation process. Okay, when the electron returns to its ground state, it comes back down. Okay, it releases a photon. Okay, so it absorbs the energy and then it releases energy when it comes back down to the ground state. Okay, and in Bohr studies, this was in the visible light spectrum. One thing to note here is that the energy that is absorbed is always more than the energy that's released. Okay, so it takes more energy to excite it than the energy you get back after the electron drops back down and gets released. Okay, and a lot of that's kind of like the principle of whoops, didn't mean to do that. It's the principle of kind of fluorescent microscopy. Okay, so even Bohr's model is not perfect. The main problem with Bohr theory was that the system of atoms larger than hydrogen. His theory worked great for hydrogen. Anything bigger than hydrogen, his predicted spectra, like where the lines would be, were wrong. Okay, there are always more lines than what Bohr predicted. So there's something else that Bohr was missing, and that is something to talk about when I get back. Okay, so I should be back tomorrow. Hope you're all having a great day. So it's just going to be a couple of textbook questions. I have them posted on CBLE, and the spy teacher hopefully can just read one more for me. I think I have their notes. Okay, have a great day, and I'll see you tomorrow. Bye.